Okay, so we'll get started. So next week is Thanksgiving, right? So yes. So obviously we're not going to have class, and so I think contractually I'm required to hold a makeup class of some kind because you guys have paid for 36 hours of instruction. So there will be a makeup class the Saturday. I have to finalize the scheduling and everything, but it's going to be the Saturday before the final exam. Okay, so so the final exam is scheduled for a Thursday, and then the makeup will be the Saturday before. I will record that lecture, and it will mostly be a review of concepts for the final. Okay, so I guess every class is quote optional. I never take attendance or anything. So, but I will be here, and I'll teach whether all of you show up or none of you show up. Last year, there was Thanksgiving also, and I think like 2 students showed up, and it was fine. But I'll review all the kind of the concepts, do an overview of the course, and highlight special things I think you should know for the final. So if you come on Saturday, great, and if you don't, the video will be posted and you can watch that. Okay, so.
What time will it be?
Probably the morning, so probably like 9 to noon-ish. Probably more like 9 to 11 something, because, no. Anyway, okay. But, yeah, so enjoy your Thanksgiving, and we'll see you guys in 2 weeks then, okay? Okay, so today we are covering ANOVA. This is chapter 11, and we will cover ANOVA, which stands for Analysis Variance. Okay, so the ANOVA, and there is what we will learn is one way ANOVA. This is the most basic form of ANOVA. I will mention some of the other forms in kind of the context where they apply. But yeah, we will learn one way ANOVA. So one way ANOVA is the simplest form of ANOVA, okay, and there are other versions of ANOVA. I shouldn't say versions, but we can extend ANOVA to make it more complicated. Versions that are more complicated. I will mention those, or I will kind of mention the context where they were used, their use, but we will not learn the analysis, okay? Not learn, I don't know. And also just a quick demonstration in R. Okay, and kind of like many of the topics in this course, where this is an introductory course, so it's kind of like a survey of statistical techniques and methods. You can take an entire course on ANOVA itself, okay? Usually, and for students who are interested in more statistics, and I think another class, depending on the area of statistics that you're interested in, so another class That could be a good follow-up. So this class is probably, it'll be under the title Design of Experiments and ANOVA, okay? Or something along those lines, okay? Design of Experiments and ANOVA. Usually if or it could just be called Design of Experiments, and almost certainly ANOVA will be mentioned. The class might be titled ANOVA, but usually Design of Experiments is the kind of the primary class, and ANOVA is the primary tool used in that. So you could take an entire course on ANOVA. We're just going to learn kind of the basic version of ANOVA and kind of its usage here. Okay? So big picture, which is always okay. So for with one-way ANOVA, what we have is we have a numeric response and we have a categorical predictor. Okay, and this categorical predictor, or I guess, predictor I'm putting in quotes, but the categorical predictor can have more than 2 categories. It can have only 2 categories, but if you have 2 categories in a numeric response, what analysis method can we use instead? So if you have a categorical predictor, just categorical variable with only 2, if you have 2 categories and you have a numeric response, what can we use to analyze our data? Well, I was hoping somebody would say a t-test, a t-test to compare the numeric response between 2 categories, right? So whether it's this category got placebo and this category got the St. John's wort, is there a difference in their response, the response being their the score on the ADHD scale, right, inattentiveness scale, okay, or whether it's this group of plants got antsy or whatever it is, and this group of plants got something else. Was there a difference in the heights that they grew, or whatever it might be? Okay, so and that we've covered t-tests quite a bit. We've got a numeric response and we have categorical, 2 categories there, right? With one-way ANOVA, we can have more than 2 categories. Okay, and the big picture behind ANOVA is that our response, there's variance in our response. Okay. So our response we have a numeric response variable, right? So there is variance in our response. Okay. And with ANOVA, we are trying to separate out just variance that exists because, quote, everything is different. Okay, so things are, if we select, if we select 50 people, okay, they're all going to have different heights, right? I mean, you might have 2 people that are of the same height, but in general, all of these people will be, have different heights or slightly different heights. Okay, so we have variance in our response, and we want to separate out the reasons for these height differences. Okay, we could just say, well, everyone is different height because everyone's different, right? That's kind of our baseline. We could just say, people are different. They're going to have different heights. So that's just variance. What we could do is we could try to explain part of that variance, and we could say, well, part of the reason why people are different heights is because men and women in general have different heights. So we could say, part of the reason why people are have different heights is because in general men are taller than women, and so if you see some people, they have different heights because there are men and there are women. And then on top of that, men have different heights from each other and women have different heights from each other. Okay, but part of the reason for height differences could be explained because of the existence of different sexes. Okay, and that's what we're trying to do with ANOVA. We're trying to say, whatever variable it is that we're looking at, we're going to try to split up or break apart the total variance into different pieces. One will be due to the fact that there are different groups in our population, and then the other will be just what's called residual variation, which is just the variation that exists within our groups. Okay, so that's what we're trying to do with ANOVA. Okay, so we try to, quote, break apart the total variance into components. Okay, sum of the variance results from the existence of different groups in our population. Okay, and then the rest of the variance is, just variance that exists no matter what. Okay, it could also be thought of as within group variance. Or residual variance. Okay. Okay, so maybe let me make a thing, and we'll just talk about the quote, problem of multiple comparisons. Okay, so we can let's say we have a numeric variable, okay? And in our text, it is how much an ear of corn weighs, okay? Book uses a lot of agricultural examples here, okay? And we were looking at different organic methods for controlling pests, okay? numeric variable, and then so we have a categorical quote predictor, and these are different methods to control pests organically. And I know nothing about farming, and so we have treatment 1 was they used nematodes. I don't even know what these are. Sounds like a cartoon show or something. All right, so anyway, we have all these things. We could use wasps, which apparently don't like corn, but like the pests, and then so we have 5 treatments. We had bacteria, nematodes, and wasps. Bacteria. It doesn't matter. Okay, and then a control group where we didn't use any pesticides, organic pesticides, I guess. Okay. And then and so we measure how much the different corn weighs, and we want to know is there a difference? Okay. So with 5 groups, we could, one approach is to perform multiple t-tests. Okay, because the overall question is, which method will, yield the highest corn weight, right? All right, and so so we can perform multiple t-tests, and we can we could have now test 1 will be the null hypothesis is that mu of group 1 is the same as mu of group 2, and then the alternative is that they're different, right? And then test 2 could be that we're going to test the nematodes versus group 3. So it will be mu of test 1 versus mu 3, and then test 3 will be the null hypothesis will be group 1 versus group 4. And how many tests would I need to perform here? mu1 versus mu5, okay, and then I would have mu2 versus mu3, mu3 versus, I'm sorry, mu2 versus mu4. We would have a bunch, right? mu2 versus mu5, etc., etc., etc. How many tests am I going to have to do? I have to do like 10 tests, right? I think. Etc., etc., etc. So, is it okay that I'm not writing them all out? Yeah. Okay, so we'd have to perform a bunch of tests. Is that okay? Do we see any drawbacks of this method? So you guys know how to do t-tests, and you can perform, you can say, is nematodes different from bacteria? Is bacteria different from wasps? Is bacteria different from control? All of this stuff. Problems with this other than the fact that we have 10 tests to perform? Because 10 tests, I mean, if you've got a computer, it's not very hard. You just say 1 versus 2, 2 versus 3, 3 versus 4, etc., etc. You just list all of these out. the computer can do them quickly. You can say, oh, my p-value here is significant, therefore it's different. My p-value here is insignificant, therefore it's not different. Do we have any problems here, though? Okay, let's talk about type 1 error. So what is a type 1 error? What's that? False positive. Okay, so what would a type 1 error be in the case of test 1? So in test 1, the null hypothesis says that, corn yield is the same for nematodes and wasps. Okay, so a type 1 error is rejecting the null when the null is true. So what would a type 1 error in the case of test 1 be? So type 1 error is that we conclude nematodes and wasps yield different corn weights. Okay, so we conclude there is a difference between the yields of using nematodes and wasps. Okay, but the reality is what? I don't know why, but the reality is there is no difference. The reality is that the null hypothesis is true. So the reality is that there is no difference. Okay, so that's what a type 1 error would be. What is the probability of committing a type 1 error? Alpha. Okay, so let's say we use alpha equal to 5%. What's the probability we commit a type 1 error with test 1? %, right? Not a trick question. Okay. What's the probability I commit a type 1 error with test 2? Also 5%, right? Okay. Probability of committing a type 1 error with test 3, also 5%. So I'm performing 10 tests, okay? And each test, I have a 5% chance of committing a type 1 error. So what's the probability that I emerge unscathed after 10 tests? Not good, right? Because it's like, I don't know, it's like playing some silly game where every time you play, there's a 5% chance of disaster, right? I don't know how bad type 1 error is, but let's say this is a bad thing if you commit type 1 error, okay? And you play the game 10 times, there's a fairly decent chance that one of those times something goes wrong, right? And so this is the problem with doing just a bunch of t-tests, is that if you perform a whole bunch of tests, you're almost bound to commit a type 1 error. And if we had 7 categories rather than 5, we would have 21 tests to perform, okay? So we had 21 tests to perform. It's very, very, very likely that at least one of our results is a type 1 error, okay? And you never know. That's the thing about hypothesis testing, is that you make your conclusion, but you don't know if that conclusion is correct or it's type 1 error, okay? If you've chosen to reject the null hypothesis. So, with each test, we've got a 5% chance of committing a type 1 error. So, with many tests, the total probability of committing a type 1 error is very high, okay? So I'll write that down. With many tests, the total probability of committing type 1 error is very high. Okay, it's not exactly all of these tests are not exactly independent of each other just because you're using the same data, so you can't just multiply 0.95 raised to the 10. But I hope you guys see that there's a high risk of type 1 error here. Okay, so so ANOVA is one way to kind of address this issue of multiple comparisons. It has its own weaknesses, okay? And I would say the biggest weakness with ANOVA is that the alternative hypothesis is always non-directional, unless you have only 2 groups to compare, okay? If you only have 2 groups, you're essentially performing a t-test. But with ANOVA, so this is one-way ANOVA. The null hypothesis is that mu1 is the same as mu2, which is the same as mu3, which is the same as, okay, so it's saying that the means of all of your groups are the same. This is your null hypothesis. All groups have the same mean. The alternative hypothesis is at least one mean is different. Okay, but this is, in this case, it's always a non-directional alternative. We might come to the conclusion that at least one of our means is different, but ANOVA does not tell us which mean is different, okay? So we might conclude to reject the null hypothesis, but ANOVA will not tell us which group has the different mean. Okay. I guess you can have a directional alternative if you only have 2 groups, and it's effectively like a t-test then, okay? So this is, we can have another formulation. Okay, so another way to write the null hypothesis. Okay. So above here, and I kind of hate to do this in your notes, is that effectively we are saying each value y, okay, is equal to the group mean plus some unknown error. Okay, so if y sub I belongs to group I, we're effectively saying the value you observe is the mean of its group plus the fact that it's there's individual variance, right? So for example, we could say the average height of men is 70 inches and the average height of women or females was 65 inches. Okay, I don't know, I'm making these numbers up. And then so we could say Joe is 6 feet tall, 72 inches. So, you know, his observation y sub I is equal to, in this case it would be 72 is equal to 70 plus an individual variance of kind of, not variance, but individual difference of 2 inches. Is this okay? So this is kind of the expression under here. Okay, so now I should write, there's another way to write the null hypothesis. Okay, and in this case we say our null hypothesis is that tau 1 is equal to tau 2 equal to, you know, all of our taus are the same and they're all equal to 0. Okay, and then the alternative, so this part looks so far the same. Okay, at least one tau is different, or is not 0, I should say. Okay, but the model is a little bit different. Okay, so here our overall model is that an individual's height, y sub I, okay, or ij, or whatever you want to call it, here is a mu with no subscript plus a tau for belonging to group I plus an error term for the individual. And so in this case, what we would say is that the overall mean, the mean height for everybody, is maybe 67.5 inches. And then we say there is an effect. We call this the group effect. And we say if you are male, the group effect is we add 2.5 inches. And if you are female, the group effect is taking away 2.5 inches. And then so if we look at Joe again, if Joe is 72 inches, what we are saying is that his height is the grand mean, the mean of everybody, plus the effect of him being male, plus his own individual difference. So we'd say 72 is equal to 67.5 plus the fact that he's male gives him a 2.5 inch quote boost per per se, plus his own individual difference, which adds 2 to that. For one-way ANOVA, either of these are fine, okay? Whether you write your null hypothesis this way or this way. It's just that as soon as you depart from one-way ANOVA, as soon as your ANOVA gets a little bit more complicated, you almost always have it written in this way, okay? Because we don't make means for every single group, okay? So if you have more than one categorical variable as being used as your predictor or whatever, it's almost always going to be written this way. Do both model expressions make sense? Are there any questions on this? Okay, so let's I'm going to explain our ANOVA, and we'll have this running example going here, and I'm going to just go into my textbook here. This is the 4th edition, and let me jump up to here we are. Alright, so I'm gonna copy this. So I'm going to use this table of data. Put this into our notes here. Okay. So what we're looking at is we have some. This is lamb. We're looking at the weight of some lambs here, and we're basically saying we're putting them on 3 different diets. Okay, there's diet 1, diet 2, and diet 3. Okay, you can copy the table into your notes if you want. You don't have to. It might be good. So under we want to know how much do these different lambs gain? How much weight do they gain under these different diets? Okay, so under diet 1, we put 3 lambs on diet 1, and they gained, one of them gained 8 pounds, another gained 16, and then another gained 9 pounds. Okay, and these 5 lambs were put on diet 2, and this is how much they gained. These lambs were put on diet 3, and this is how much weight they gained. And the question is there a difference in the amount of weight these lambs gain? Okay, or maybe the question really is, do the different diets cause the lambs to gain different weights? Different amounts of weight. Okay. And if we look, we could, if we take the average of these 3 numbers, 8, 16 plus 9 divided by 3, we would get 11. So this is just the average of these 3 numbers. Okay, so 8 plus 16 plus 9 divided by 3, we get 11, okay? And so we look at the group means, 11, 15, and 12. So our group means are different. We have 11, 15, and 12. Are indeed different. Okay, they are 11, 15, and 12, okay? But the question is, are they significantly different? Or is one of these at least one of these significantly different from the others, okay? Is at least one of these group means significantly different from the others. What do you feel? Any gut feeling here? Yes, no, maybe? Maybe, okay. Well, let's see, so maybe 15. So what I'm going to do is I'm going to create a dot plot here, all right? Okay. And so this will be diet 1, diet 2, and this will be diet 3. And then here I'm going to just put all of them together in one, okay? And so the smallest number I have, it looks like 6. So I'm going to just put 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. Okay, so we'll do that. Let me just kind of give myself some guidelines here. I should do it on just the even ones. They're supposed to be equally spaced. Okay, so now I'm just going to put these dots up here. Okay, so on diet 1, we have a lamb that gained 8 pounds. And a lamb that gained 16 pounds. And a lamb that gained 9 pounds. Okay, and the mean of these 3 lambs, I'll put in a little red line, is 11. Okay, so this is its group mean. And then on diet 2, we have a lamb that gained 9 pounds, one that gained 16, one that gained 21, 11, and 18. Okay, and so its group mean is right here at 15. And with diet 3, we have a lamb that gained 15 pounds, 10 pounds, 17, and 6. Okay, and so its group mean is 12, which goes right here. Okay, and if we if I put all of these dots together, then I have my dot plot looks like this. And the overall grand mean, okay? So we have this concept called the grand mean, y double bar. This would be equal to, if we add up all the data points, so we have a total of 12, so this would be the average of all data points. Okay. Now we have to be careful to do the average of all data points, we cannot do the average of averages, okay? So I will say do not take the average of averages. Okay, because the average of averages would assume that all groups are the same size, which is not the case, okay? We have to kind of weight these. So if we wanted to add them all up, we would have to add up all 12 and we would divide by 12. But we might not, depending on, not all of the data might be available to us, okay? The only data that might be available to us would be the summary statistics, okay? So we might only have group 1, group 2, group 3, and this is how many people we had in each group. And so our grand mean, we can kind of recreate these by taking the size of each group and multiplying it by the mean of that group. And then we can add them up, all of these things, and divide by how many data points we had. Okay, so in this case, we could do 3 times 11 plus 5 times 15 plus 4 times 12, and we would divide by 3 plus 5 plus 4, which is 156 divided by 12, and so my grand mean is 13. Is that okay? And so, so the grand mean, I'm going to draw a blue line, is right here. So this is the grand mean. So if we average all the data points together, the grand mean is 13. And we want to know, are any of these group means significantly different, basically, from the grand mean of everything? So looking at our plot now, how do we feel? Maybe, maybe not. Okay. So just kind of taking into account that of the individual variation that does exist, it seems like there's a lot more variation just from lamb to lamb than there is between diet to diet, at least with this many data points. Okay. Are there any questions so far? Okay, can I flip to the next slide? Okay, so let me, let's see, what do I want to copy here? I'm going to copy this, yeah, actually I want both of these things here. Okay, I'm going to just copy everything. Okay. And get rid of all of this. Okay, so I'm going to build, we're going to create what we call an ANOVA table. And what we're going to do is we're going to look at each individual data point. And we're going to say, hey, look at this guy right here. This guy is the total amount he differs from the grand mean, right? So let's let me backtrack a tiny bit. Do you guys remember variance, the formula for variance? Variance of x, which is basically standard deviation squared. You guys remember? Or not x, I guess y. Whatever, it doesn't matter. The variance of a sample of data is we take each data point and we subtract off its difference from what? From the mean, right? So y bar, and what do we do with it? We square it, we add them all up, and we divide by n minus 1. Okay. So what we're going to do is we're just look at this numerator here, okay, and we have y minus y bar. And so that is effectively how different, if we're looking at the total variance here, we can think of each data point, you know, how different is each data point from the grand mean? Okay, that's okay. How different is each data point from the grand mean, and then squared is effectively what we're going for. Okay, so how different is each data point from the grand mean? That quantity squared. So we're going to say, hey, look at this data point right here. Okay, this data point is 9. Okay. This guy is how far away from the grand mean of 13? He's 4 units away, okay? But we can kind of break that apart, and we can say, well, his group is 2 units away from the grand mean, okay? So we're gonna break it apart into, say, some of this difference is the fact that his group mean is different from the grand mean, okay? So we say, okay, his group mean 2 units away from the grand mean. And then he himself is still further, another 2 units away from his own group mean, okay? So that difference of 4 units from the grand mean is broken out into 2 parts. His group mean is different, and then he himself is different from his group mean. Okay. And we're effectively going to do this breaking apart for everybody. Okay, so for all of the data points. Okay, and so what we have is just looking only at the numerator part, we're going to deal with what we call the sum of squares. Okay, so let's see, where can I write this? So total variance. Okay, so well, let me see. So we break apart this deviation. We break apart the difference from the mean into 2 parts. Into 2 parts. We say the lamb's group is different from the mean. Okay, so there is a difference between the y, the group mean, y bar, minus the grand mean of y double bar. Okay? And then we say the lamb itself is different from his group mean. Okay, and so we have y, the individual data point, is different from his group mean. Okay, and so this, the total difference is, you know, the difference between the individual data point and the grand mean. We can see, you know, we have the total difference is the individual data point minus the grand mean that can be split up into these two parts. Is that okay? All right, and so we'll do this, you know, with formulas here. Can I flip to the next slide? Okay. So I'm gonna break this apart into two parts, and we got. Okay, so we'll say. So part of our table, we're going to have what we call the sum of squares, and we're going to break this out, the source. Okay, so the source will be, we're going to call part of this the between group variation, and we'll have this within the group. So this is the fact that the group is different from the mean, and then the within group, or this is also known as the residual. Okay. So if we think of the sum of squares here, this would be each group mean, y bar minus the grand mean quantity squared, right? Okay. How many all three of these data points here would have the same value for y bar minus y double bar, right? All three lambs in diet 1 would have the same y bar minus the grand mean, right? They would all say, my group mean is 2 less than the grand mean. All three of them would say that. Okay? And so we would take this quantity and I can multiply it by n, the number of data points in the group, and I would sum this up for all groups. Is that okay? And then within the group, we would take each individual data point y sub I, and we would subtract its own group average. So we would say this guy is 2 away from his group average, and we would square that difference, and we would add them up for all data points in the group, and then we would have to add them up for all groups, right? So one sum for all data points in the group, and then do it for all groups. Okay. And then the sum of squares total, the total sum of squares would just be each individual data point minus the grand mean, and we would square it, and this would be for all points in the data set. Is that okay? So I'm just going to kind of demonstrate that it works. Indeed, it works for all of the data points in diet 1. I'm not going to do it for all 12 data points. That would probably take too long. Okay. But we can make sure that that this works here. Okay, so let's do this for example with diet 1. Okay, so we say you know, this lamb here, 8 pounds. Okay. So let's we'll do the total sum of squares. So the grand mean is 13. So we're going to say 8 minus 13 quantity squared, plus the next guy weighed gained 16 pounds versus the total average of 13. And then the last guy gained 9 versus the total average of 13. Okay, so this is kind of the total sum of squares contributed to the total variance. So, okay, so I have 5 squared plus 3 squared plus 4 squared. And so what's that? 50 points? 25 plus 9 plus 16. Yeah, I think that adds up to a total sum of squares of 50 contributed by these 3 data points. So far so good? Okay. All right, so let's do how much of this total sum of squares can be attributed to the fact that the group was different. Okay, so if we look at each data point, or the group's mean is 2 away from the grand mean, right? The group's mean is 11 and the grand mean is 13. So the group mean is 2 away from the grand mean, so we square that difference, and then we do it for all 3 data points. But all 3 data points are going to have the exact same 11 minus 13 squared. So I can just multiply this by 3. So this gives me 12. I think 3 times 4. So I get a total sum of squares between the groups, at least for group 1, that portion adds up to 12. Okay, and then lastly, let's look at this within group. Okay, so within the group, the first lamb is gained 8 pounds versus his group average of 11. So we're going to square that difference. The next guy gained 16 versus his group average of 11. And then the last guy gained 9 versus his group average of 11. Or her, whatever. So 8 minus 11 squared would be 3 squared, so well, I'll just write 3 squared. And here we've got 5 squared. And here I've got 2 squared. Okay, so this is 9 plus 25 plus 4. And this adds up to 38. And so indeed we see this plus this equals this. So the total sum of squares can be SST, the total sum of squares can be broken out into sum of squares between plus sum of squares within. Okay, and you know, we could do the same thing for diets 2 and diets 3, and we would see that the total sum of squares can be broken out into those 2 parts. Okay, so I mean, just based on this by itself, you know, what's kind of your gut feeling in terms of, does it seem like the amount of variation contributed from the fact that the group mean is different, is that large or small in comparison to the variation that just exists within the group? It feels small, right? Because the amount of variation contributed by the fact that groups are different, we've given, you know, it has the number 12, and then the amount of variation that exists just from the fact that individuals are different within a group is 38. So it seems like just the fact that individual differences are big seems to contribute a lot more. Okay. But anyway, we can complete our analysis here. Okay. So I'm gonna can I go to the next slide here? Okay. So just carrying this on, I'm gonna put a copy what I had before. So we had the source, we had between, And within our residual, and we had total. I'm going to add a column here called degrees of freedom. Degrees of freedom for the total is total number of points total minus 1, okay? Or to indicate number of points total, we do n dot to include all of this. So we would have, in our case, what would our degrees of freedom be? We have a total of 12 data points, so we would have 11 degrees of freedom total. Okay. The between group variation is basically the number of groups minus 1, which symbolically we write I minus 1. So in our case, how many degrees of freedom do we have here? 2. Maybe I'll draw kind of a pencil line to separate these. And then within the groups, it's basically just this plus this have to add up to each other. But you have n dot minus I. So in our case, it's just whatever 2 plus what must add up to 11. We're going to stick in 9. Or you could say 12 data points minus 3 groups also makes 9. Our sum of squares. So over here, we've established that sum of squares is n times y bar minus y double bar squared. Let me just kind of... And then, and over here I said we take each individual data point minus its group mean, and we square it, okay? But this requires that we know each individual data point. And sometimes, you know, if you have lots of data, this is not available to us. So we have a little bit of a shortcut to get this, okay? So let's think back to you know, what variance and standard deviation is, okay? So if I square my standard deviation, I have variance, right? And that is equal to the sum of y minus y bar squared divided by n minus 1. Is that okay? And so this part, this numerator up here, is exactly what I have right here, right? So I could multiply both sides by n minus 1, and this gives me the numerator. And so that's what I'm going to do. I'm going to replace this part, including the sum, with n minus 1 times s squared, okay? And so this sum represents, do this operation for what? For all groups. I no longer have to do it for all data points within the group if I'm given the standard deviation. Is this okay? And as far as our analysis goes, okay, naturally what happens is as you have more degrees of freedom associated with one of these sources of variation, this sum of squares gets to be really huge. or it could be really huge. So we create a quantity called the mean squares, okay? For mean squares. And this is just the sum of squares, this quantity sum of squares divided by the degrees of freedom. Okay. Let me actually move this. And then lastly, to decide if something is significant or not, we use a value called the F statistic. I don't want to get into all of the details behind the F distribution and how it works, but when you run ANOVA on the computer and things like that, you're going to see this number F statistic, and this is how we decide if something is significant or not. And this is equal to the mean squares of our row. So in this case, mean squares between, divided by mean squares residuals. Okay. And so the ratio between the mean squares here is what decides whether or not the source of variation is significant. So it's kind of a ratio between, so we can think of this residual as kind of the background variation. Like this is just background noise that exists. You know, individual lambs are different from each other. That's something that we can't avoid. What we want to know is if the diets are causing a certain amount of variation. And maybe they are, maybe they aren't, okay? And we're going to make a decision about that based on whether kind of this mean squares value, which is the sum of squares due to that source of variation divided by its degrees of freedom, if that is large in relation to the mean squares, kind of the average amount of sum of squares that exists from that exists for each lamb. Okay, so the degrees of freedom, it's not exactly this, but you can kind of think of this as, so we have a total sum of squares, and I can divide the total sum of squares by not exactly this, but every single lamb that we have. Okay, and then we also have a total sum of squares between the group, and I can divide this by not exactly this, but how many groups we have. So we're kind of sharing the total sum of squares. We're dividing this by kind of like how many groups we have. And we're taking the residual sum of squares and we're dividing it by kind of how many data points we have. So it's like the average sum of squares for each data point, the average sum of squares for each group, kind of like that. That's the idea behind mean squares. And then we take the ratio between those two. And we want to know, is that big or is that small? Okay? And then so once we get this, we can look this up in the F table or ask the computer what, is this statistically significant or not using the F distribution. Okay? F distribution, it's technically a ratio between two t distributions, and it's developed by Ronald Fisher. He can be thought of as the father of modern statistics. And so it's named after him, the F. If you're interested on the math side, so if you like calculus and proofs and all of that, you can take a mathematical statistics course, which gets into kind of the proofs behind these distributions and why, in our class we kind of just say, this is how you do the test. You get this number, you look it up in a table. But we don't really explain where these tables are coming from. We just kind of say these tables are here. And a mathematical statistics class will kind of explain where the tables are coming from. And so if that's of interest to you, you can take what's called mathematical statistics. Okay, so we'll finish our example here, getting our degrees of freedom, our sum of squares, our mean squares, and our F statistic here. Okay. So, whoops, yeah, that's what I want. Okay, so we'll go through. So our source, so is between, and residual. And we don't really even need to bother with the total table, but we could. Okay, so our degrees of freedom, what do we have? We got 2 degrees of freedom between number of groups minus 1. Total degrees of freedom is number of data points, 12 minus 1. And so our residual degrees of freedom is 9. Our sum of squares is we take the group mean, right? So we do y bar minus the grand mean of 13. We square that and we multiply that by n, and we do that for all groups. So we have 3 data points in our first group, and we have a difference of 11 minus the grand mean is 13. And then we do this for all groups, so we do 5 times the difference of 15 minus 13, and 4 times the difference of 12 minus 13 squared. So this ends up being 3 times 4 plus 5 times 4 and 4 times 1, right? 2 squared, so we get 38. Now I need let me rewrite this, sorry, or just slide this down over so I don't run out of space. And then over here we have n minus 1 times s squared. So I do 2 times 4.359 squared plus 4 n minus 1 times 4.95 squared, and 4 minus 1 is 3 times 4.967 squared. And when I do that, what is the number I get? 210. Okay. So our mean squares is going to be sum of squares, 38 divided by the degrees of freedom, 2. So I get 19. And the mean squares here is 210 divided by degrees of freedom, 9. So I get 23.33. Or did I add something up wrong? I did. This is 36. Nobody caught me. Sorry, okay. So this is 12 plus 20 plus 4, yeah, it's 36. Okay, so my mean squares is 18 and 23. And then so our F statistic is 18 divided by 23.33. And this is equal, you don't have an F for the residual, okay? So 18 divided by 23.33, 0.77. Okay, how's this feeling? It feels like a lot of work. well, what we're doing is we're trying to separate out. If we measure the total variance as the total sum of squares, we're splitting that out into two parts. Okay, the part that can be attributed to the fact that the groups are different from each other, and the part that it is just attributed to the fact that individuals, even within a group, are different from each other. Okay? And yeah, so it is a lot of work. We generally use a computer. We throw all of these things at a computer and say go, and the computer does it very quickly for us. But I think it's useful to, I think it's very important that we know where the numbers that the computer gets are coming from, and I think just kind of from a practical standpoint, it's useful to learn this as far as these formulas go and stuff. But yeah, the big concept is we're separating out the total sum of squares into these two components, and then we're taking a ratio between the kind of the average squares, mean squares between the two components. Okay, and so at this point we've got an F statistic, and we can look this up in an F table. Okay, and so you do not have an F table as part of your reference packet, so I will show you how to use the F table. So the 4th edition of the textbook came with F tables. The 5th edition of the textbook does not. And they say go to our website and download these tables. Or you can go online and look up F tables. But the F tables in our textbook and the F tables online, they're not all exactly the same. So let's just take a look at our F statistic, and I'll show you how to use an F table if ever you want to do this manually. And that's how we go. Okay, so when we look up an F statistic, you need you need 2 degrees of freedom. Okay, there's a numerator degrees of freedom and a denominator degrees of freedom. So you have a numerator df, which is sometimes called v1, and you have a denominator df, which is sometimes called v2. Okay, so it's just how many degrees of freedom are associated with the numerator, in our case 2. How many degrees of freedom are associated with the denominator? 9. So that's straightforward. And we would use these to look up our F statistic in an F table. So if you ever had to do this. Okay. Alright, so I'm going to go, so first I'll pull up the F table in our textbook, and what is it? It's like way out here. So let me, okay, so the F statistics, the F table in, at least in the 4th edition of the textbook, starts on page 628, and then it's multiple pages. You've got one page for each numerator degrees of freedom. It says numerator df equal 1. There's another page for numerator df equal 2, numerator df equal 3, and it goes all the way up until numerator degrees of freedom equals 10. So you can have up to 10 degrees of freedom. And then so anyway, you find the table with the correct number of numerator degrees of freedom, and then you find the row with your degrees of freedom, 9 in our case, and it says here are the critical values. Okay, and so if we look up our test statistic of 0.772, we would say, oh, 0.772 is less than 1.93, therefore our p-value is greater than 20%. Is that okay? So in our case, it would be like that. are there any questions on using this F table? So you have the numerator degrees of freedom, the denominator degrees of freedom, and then you compare your F statistic, just like using the chi-squared or t-table, and you say, well, how does that compare to our tail probability? It says, oh, 0.772 is smaller than this number, therefore our tail area is greater than 20%. Is that okay? All right. If you ever go online, whoops, and you look up an F table, okay, chances are you're going to get something that looks like this. Okay. So you look at this thing and you're like, what is this? Where are these? Huh? I missed something. View image. Okay, so this is small. Okay, so it says numerator degrees of freedom. Okay, so we have 2, and it says denominator degrees of freedom, we have 9, right? And what this says is these are the critical values for when alpha is equal to 0.05. So in our case, what we're doing is we're going to our number is 0.772, okay? And so in our case, we look at here and we say, oh, 0.772 is smaller than 4.25. Our result is not significant at the 5% level, okay? If we get F is equal to 5, then we would say 5 is bigger than 4.25. F is significant, our test is significant at the 5% level. Okay, and then we could look at this one, same type of thing, and this is with alpha equal to 0.01. So with numerator degrees of freedom 2 and denominator degrees of freedom 9, if we have, our F is equal to 5, it's significant at the 5% level. That was the other table, but it's not significant at the 1% level. So here it's just kind of like, is your number bigger or smaller than this? And that's what we have. So I'm hoping these line up. So yeah. So at the 1%, it says here it's 8.02, and that's what we have here. At the 1% level, it's 8.02. Okay. So effectively, this table is just taking this entire column, and then it's just taking this column, and then it's attaching it to this column over here. So each column here is effectively just this column right here at the 1%, and then and this one over here is the same idea. Each column is just this column for the 5% thing. So is that okay? So if you ever take another statistics class, you might see F tables written like this, where you've got numerator degrees of freedom on the top, denominator degrees of freedom on this side, and then and this is with alpha equal to 0.01. So the intersection of 2 and 9 is 8.02. So if you want your test to be significant at the 1% level, your F statistic has to be larger than 8.02, is basically what it's saying. Otherwise, it's not significant at this alpha level. And so
what that is saying is that the difference is significant, the variation.
So what that's saying is that the variation due to this source, the between groups variation, is significant. Right now, our F statistic is quite small, so it's saying this source of variation is not significant.
The groups again are the diets.
The groups are the 3 different diets that we have. So we are saying so here, this is good. I'm going to go to the next slide. And so the results of our test was that our p-value was greater than 20%, okay? Or, is not significant at the 5% level or 1% level. And so effectively what we say is the variation due to the different diets is not statistically significant. Okay, so the variation due to the different groups, or in our case, the different diets, is not statistically significant. And so we would say we do not have evidence that the means of each group, of the different groups, are different from one another. Okay, why don't we pause here? We'll take a 10-minute break, come back at 9:01, and finish out.